Welcome, diamond valuation enthusiasts, to a brilliant journey in our machine learning series. I'm excited to be here with you, and today we're diving into a regression task using a sparkling dataset and a powerful explainability tool. I'm running this in Google Colab, breaking it down into clear code blocks so you can follow along as we predict diamond prices with precision. Let's get started by setting up our environment and gathering our tools for this gemstone adventure. I kick things off by installing the required libraries in Colab with pip3 install interpretLime. These libraries are essential for explainable AI, helping us uncover the reasoning behind our model's predictions. Next, I import the core dependencies: NumPy for numerical operations, pandas for data manipulation, and Seaborn to load our dataset. From Sklearn, I bring in train-test-split to split our data, random forest regressor for our model, and our to_score and mean_score_error to evaluate performance. From interpret, I import the show function to display explanations, and from interpret.blackbox, I import LimeTabular, our tool for local explanations. I set a random seed with np.random.seed42 for reproducibility. With our toolkit ready, let's load the data and start exploring. I load the diamonds dataset using Seaborn's load_dataset function, pulling in the diamond dataset. I print df.head to take a look. The first row shows carat 0.23, cut ideal, color E, clarity SI2, depth 61.5, table 55.0, price 326, X 3.95, Y 3.98, Z 2.43. The next row has carat 0.21, cut premium, price 326, X 3.89, Y 3.84, Z 2.31. This dataset contains 53,940 records of diamonds, with features like carat, weight, cut, color, clarity, depth, height percentage, table, width of the top, price in US dollars, and dimensions X, Y, Z, length, width, depth in mm. Prices range from $326 to $18,823, making it a diverse dataset for predicting diamond values. I select only the numeric features for simplicity. X includes carat, depth, table, X, Y, Z, and Y is price. The target will predict. I print x.columns to confirm. Carat, depth, table, X, Y, Z, exactly what we need. Let's move on to splitting the data. I split the dataset into training and test sets using train-test-split, allocating 20% for testing and 80% for training, with random state 42. This gives us 43,152 training samples and 10,788 test samples. The selected features, carat, depth, table, X, Y, Z, are all numeric, and the dataset has no missing values, so no pre-processing is required. The target price is also numeric, with a wide range that will challenge our model to capture pricing patterns effectively. We're now ready to train our model and see how it performs. I initialize a random forest regressor from Sklearn with random_state42. Random forest regression is an ensemble method that constructs multiple decision trees, 100 by default, each trained on a random subset of the data and features. It averages their predictions to reduce overfitting and improve accuracy, making it a robust choice for regression tasks like predicting diamond prices, where features like carat and dimensions may have complex, nonlinear relationships with price. I call fit on X-train and Y-train to train the model, letting it learn how features like carat and X influence diamond values. Once trained, I make predictions on X-test with predict, storing them in Y-pred, and evaluate with R-squared and mean-squared error. The results are strong. R-squared score is 0.8805 to 88.05% of the variance explained in the test set, a solid performance. Mean-squared error 1,898,883.0475. Root that, about $1,378, which is reasonable for prices ranging from $326 to $18,823, though it indicates some room for improvement on high-value diamonds. I use LimeTabular from Interpret's black box module to explain our model's predictions. LimeTabular is an explainability tool based on Lime, local interpretable model-agnostic explanations, which provides local explanations for any model, in our case, a black box random forest. It works by perturbing the input data around a specific instance, fitting a simple interpretable model, like linear regression, to approximate the black box model's behavior locally, and then showing how each feature contributes to the prediction. I initialize LimeTabular with rf_predict as the model, xtrain as the background data, the feature names from xtrain.columns, and random_state42. I generate local explanations for the first 5 test samples with lime.explainLocal on xtest slice 0 to 5 and ytest slice 0 to 5. I extract the explanation data for the first record with local explanation.data 0 and print the details. Predicted 563.76, true value 559, extremely close, only $4.76 off. Feature contributions show caret at minus 3,034.65, the strongest negative push, significantly lowering the predicted price, likely due to a small caret value. Y at minus 1,090.24, X at minus 334.10, and Z at minus 201.47 also reduce the price, while depth at 156.45 and table at 105.67 push it up. On screen, you're seeing the local explanation plot, a bar chart for this prediction. The caret bar juts far left in blue at minus 3,034.65, heavily lowering the price. Small caret, small price. Y, X, and Z, also in blue, add minus 1,090.24, minus 334.10, and minus 201.47, further reducing the value. Depth and table, in orange, stretch right at 156.45 and 105.67, increasing the price. The final prediction of 563.76 is marked at the top, a clear breakdown of how features shape this diamond's value. Let's reflect on these outputs. They're a pricing guide for our diamond market. The head showed a diamond with caret 0.23, depth 61.5, table 55.0, X 3.95, Y 3.98, Z 2.43, price 326, and another with caret 0.21, X 3.89, price 326, small carets, low prices, setting the stage for our analysis. The selected columns, caret, depth, table, X, Y, Z, focus on numeric features, simplifying our task. The R-squared score of 0.8805 means our model explains 88.05% of the price variance in the test set, and a mean squared error of 1,898,883.0475 translates to an average error of about $1,378. Decent for prices spanning $326 to $18,823, but larger errors on high-value diamonds may be skewing this. The local explanation predicted 563.76 against a true 559, with caret, minus 3,034.65, drastically lowering the price, likely a small caret, similar to the head 0.23 for a 326 price. Y, minus 1,090.24, X, minus 334.10, and Z, minus 201.47. Also reduced the price, reflecting smaller dimensions, while depth, 156.45, and table, 105.67. Push it up, perhaps optimal depth and table values for this diamond's cut. LimeTabular's local explanation provides that XAI clarity, showing exactly how each feature contributes to this price prediction, making our random forest decision transparent. To wrap up this diamond pricing journey, we've analyzed the diamond's dataset, a 53,940 record study of diamond characteristics, and trained a random forest regressor, achieving a test R-squared of 0.8805 and a mean squared error of 1,898,883.0475. The local explanation via LimeTabular revealed caret as the dominant driver for a predicted price of 563.76, with depth and table providing positive adjustments, offering a clear view into our model's reasoning. Random forest regression's ensemble approach captured complex pricing patterns, and LimeTabular's Lime-based method provided transparency for our black box model. Grab this code, experiment with additional features like cut or clarity, and dive deeper into diamond valuation. I'm captivated by this gemstone analysis. Hope it's got you thinking about data's role in pricing precious stones. See you next time for another dazzling data exploration.